So, in the last classes, we were discussing about the different components of genetic algorithm, the selection procedures available, the crossover procedures available, the mutation procedures available, etc. That we were discussing, and only the main procedures that are all, or the main methods that are being adopted in genetic algorithms were discussed in the class. And there are obviously other not so popular, not that much popular methods are also available and being implemented in different works in literatures, works available in literatures. Now, in this class, we will be discussing about the fitness scaling. What is the importance of fitness scaling? What is fitness scaling? How fitness scaling is done? The different methods of fitness scaling. So, let us see some of the issues with our fitness values that is available in genetic algorithm. That is when we calculate the fitness values in genetic algorithm. What is the main issues that is present? So suppose we have a condition like this. That is this is the condition, that is the search space is like this. The search space is in this direction. We are giving the search space, and the fitness values are given here, and the fitness values actually moves like this as the search space is moving towards the right side. That is in this case what we are considering is only a single dimensional search space. That is only in the x direction the search space is there. So this is to represent the things. It is easier to consider a low dimension search space. That is in this case it is a single dimension search space. So as the search space moves like this, or as the value of the variable or the value of the variable that is represented in this particular dimension varies in this direction, that is it increases towards right. Commonly we take towards the right in the x-axis, it increases. As it increases, the fitness values goes like this as this curve represents. It goes up and down, and here there is a peak. At this position there is a peak, then here is a drop, then again here is another peak. So here is a low, this one is a low, and here is a peak. This is the global best position, the global best position that we are searching for. Then again it reduces to some other low value. Okay, currently our current individuals are represented as the red dots. The fitness values of our current individuals, that is current population, is represented as red dots. Suppose in that case, if the red dots or the fitness values varies only from this value to this value, that is the values represented like this value to this value, the values varies. The best individuals are concentrated at this position. So in this case, actually, it has a wider range of values. That is from here to here. The values are varying. The values of the fitness values are varying. But still, the problem is there are many individuals which are concentrated with a high fitness compared to the other values, compared to the other individuals, the high fitness. So what happens is when we do the selection procedure, for the next generation, in order to transfer these chromosomes or these individuals to the next generation, most of the individuals selected will be from this condition, from this position, or within this range. A very few number of individuals will be selected from this range, because the value is very low, the fitness value is very low. So what will happen is that most of the time the genetic algorithm will stuck, or the individuals will stuck towards this region. It will be stuck towards this region, and there is less chance of an individual escaping from here and reaching here. So there is very less chance. So that is an issue with the fitness values, when the range of fitness values even if it is a wider range, one of the problem with this fitness values is this case. Then another issue with the fitness is, suppose in this case the range of fitness values is very low. See here, this is the maximum value, the green line, that is the maximum value, and this green value is the lowest value. So the this value will be won't be changing much. So in this case, the fitness values are with a narrower range of values. So what happens is, during the successive iterations, there is less chance of an improvement from this range. It is because almost all the individuals are having almost equal probability of being selected, or almost equal fitness values, and hence there is less chance of it escaping from here, moving towards this side, the individuals moving towards the right side. And most of this most of the individuals or the generated offsprings also will be within this range. So that is the issues with the fitness. So then again, the other problem with this fitness value is, even if it tries to improve the fitness values, there is a chance of premature termination. That is because in most of the cases we select the termination criteria as the average fitness values, or the change in fitness value on successive iteration, etc., etc. So if we consider the average fitness value as the condition for termination, one of the termination condition is the average fitness value and the maximum fitness value, the maximum available fitness value as well as the average fitness value. The difference between these two is very minimal. So that sort of condition, in this case, that sort of condition exists. That is, the average fitness value will be somewhere here, in between these two, that is somewhere here, and the maximum fitness is this. So the difference is only this much, very small value. So there is a chance of premature termination. That is, the algorithm will terminate prematurely, that is without finding the global optimum condition. So, or it doesn't undergoes sufficient number of iterations in order to escape from this particular scenario. So that is another issue with our normal fitness values, in most of the fitness values. So the issues with the fitness that we have observed, that if the fitness values are too far apart, then it will select several copies of the good individuals, and many other worst individual will not be selected at all. That is the condition. So if the range of fitness values is too large, and many individuals are having the higher fitness values, and many individuals are having the worst fitness values, then the chances of the worst in fitness values, or the weak fitness values, or the low fitness values, individuals with the low fitness values will not be get selected. That is a condition. So again, what happens because of this is, the entire population will be filled with very similar chromosomes, and thus will have a limited ability to explore the search space. So the ability of the GA is limited by this particular behavior. That is, the population is filled with, or the major portion of individuals within a particular genetic algorithm or a particular population is having similar chromosomes. So it doesn't explore the entire search space. So then other condition, if the fitness values are too close to each other, then the GA will tend to select one copy of each individual. Consequently, it will not be guided by small fitness variations. And again, the search scope will be reduced. By this reduction in the search scope, the premature termination is possible. So that is the issues with the fitness. Then what we will do with, or how we can overcome this particular condition, that is these issues with the fitness. So it is the answer to this particular question, that is how we will overcome these issues. it is fitness scaling. So the purpose of fitness scaling is to reduce the effect of fitness outliers in the population. That is, there will be some fitness outliers, when we discussed about the rank selection procedure. One of the chromosome or one of the individual was having a very high value of fitness value. High fitness value was there. So in that case, if we do a selection procedure without doing anything to the fitness, then what we will be having is in the next generation or in the next population, we will be having a multiple number of copies, a number of copies of that particular individual, and the individuals with the lower fitness values will not be get selected also. So that is the difficulty. So the purpose of fitness scaling is to reduce this effect. One way is to reduce this the effect of fitness outliers is the rank selection procedure. So the other way, that is in the rank selection procedure, we have to rank the chromosomes every time we are doing the same thing, even for selecting 2 chromosomes for the crossover operation. In that case also, you will have to do that ranking procedure. But if you do a fitness scaling procedure, it will be comparatively easier, because in a population you can create that particular fitness scaling operation once and then use that particular fitness values for further applications. So then the process of scaling is intended to maintain selective pressure as the overall performance rises within the population. So when the overall performance rises, that is most of the individuals are having a higher fitness values, that is towards the end of the genetic algorithm, that is towards the end of the search procedure. What will happen is most of the individuals will be having a relatively higher value of fitness. So in order to maintain the selection pressure in that particular condition, it is better to keep a fitness, or in order to keep the selection pressure constant, or maintain the selection pressure constant throughout the genetic algorithm procedure, it is always better to give a fitness scaling. So the fitness scaling mechanism is used to distinguish the performance of individuals when improvement among the population is minute. That is the change in fitness values. The change in fitness values of individuals within a population is very minute. In that case, the scaling mechanism can be used. So instead of selecting the parents based on raw fitness value X, we select the parents based on some function of raw fitness value. So the raw fitness value is the fitness value that is effectively that is available with us. That is the fitness value that is not scaled. The original fitness value, that is the raw fitness value. So we take the raw fitness value, that is the original fitness value, as X. If the original fitness value is X, then we consider a function of X, that is f of X. This f of X will give you the scaled fitness value. So the fitness scaling is used to scale the raw fitness values, so that the GS is a reasonable amount of difference in the scaled fitness values of the best versus worst individuals. That is, by doing this fitness scaling, actually what we are doing is we are creating, or we are keeping a reasonable amount of difference between the worst as well as the best individuals. But in some cases, like when the fitness range is very large, when the range of fitness values within a population is very large, the difference between the best fit and the worst fit values, the fitness values of the best fit individual and the worst fit individual, will be very large. In the case of very low range of values, very low range of fitness values within the population, the difference values, the difference between the best fit and the worst fit, will be very low value. So in these two cases are actually conflicting conditions. So By doing the fitness scaling, what we do is we keep these differences in a reasonable range, even if the value is very large or the value is very low. So that is the condition. So in fact, fitness scaling is a sort of discriminating operation in GA. That is the difference, how to discriminate between different individuals in a GA. That is the fitness scaling procedure. It is useful to avoid premature convergence and also slow finishing. And premature convergence is early finishing. That is, it is the algorithm is terminated very early without giving you the proper value, the proper optimal value. And the slow finishing is it is taking too much time to finish it. The algorithm is taking going on, and it takes too much time to complete the algorithm. So that is the slow finishing. So in order to overcome these two conditions, you can use the fitness scaling. So then the types of fitness scaling, there is 3 different types of fitness scaling is available in the literature. The first one is linear scaling, which is the mostly used one and the simpler one also. Then the sigma scaling as well as sigma truncation. The linear scaling has some limitations, and in order to overcome those limitations, the sigma scaling or sigma truncation method is used. Then the last one is the power law. It is very simple actually. So let's see the different types of fitness scaling one by one. In the case of linear scaling, that is the fitness values of all the strings such that the best individual gets a fixed number of expected offspring. That is the condition. So the linear scaling, what linear scaling actually does is it adjusts fitness values within a specific range in such a way that the best individual within that particular population will get a fixed number of expected offspring. Whether it is, it can be 2 numbers. That is, the best individual will be having 2 copies of the same copies of that particular individual in the next generation. So that way we are doing. So that number we have to fix initially in some cases. In some way of doing the linear scaling, we have to fix that particular values initially itself. Then the other values are altered so as to ensure that the correct total number of new strings are produced. That is, an average individual will still expect 1 offspring. That is, the other values, the best fit individual will be having a fixed number of repetitions of that particular string, that particular individual within the next generation. Then the other values, the other fitness values are then changed in order to ensure the correct total number of individuals. That is, the population size will be limited in itself with a chance of the average individual being present in that particular population. That is an average individual, that is an individual with an average fitness will be present in that particular individual. Mostly it will be present only once. That is the condition. That is how the linear scaling is done. So in doing this one, what we do is we limit the exceptionally fit individual, that is the best individual, to take over quickly. That is, more number of copies of the best individual is prevented from the next generation. That is, the next generation will be having only a fixed number that is decided by us before the linear scaling itself will be present. That much number of individuals will be present in the next generation, and more than if we doesn't do the fitness scaling, there is a chance of more number of instances of that particular string present in the next generation. So the way in which the linear scaling is done, or the relation that is used in the linear scaling is f dash equal to af plus b. If the linear relation between the scaled fitness, so f dash is the scaled fitness, and a is a constant that we have to determine, and f is the raw fitness, the original fitness value, then B is another constant that also we have to decide. So A and B are the scaling coefficients that we have to decide. And depending on the values of A and B, the F dash value obviously varies. The F dash value is the scaled fitness. The scaled fitness value varies with respect to A as well as B. So we have to find out the coefficients A and B. There are multiple ways of determining A and B, but one method that is available in our reference text that we will discuss. So in all the cases, whatever be the case in which A and B are selected, this condition should be satisfied. The average fitness value of the scaled fitness as well as the average fitness value of the raw fitness should be equal. This is in order to ensure the presence of an average individual in the next generation. So that is, an individual with the average value of fitness will have to be selected for the next generation. In order to ensure that particular condition, what we do is we keep F dash average, that is the average value of the scaled fitness values, as well as the average fitness value of the raw fitness value. The average value of the raw fitness values are kept equal. So in this case, as I said earlier, the number of copies of the dominant individual is kept constant, or it is controlled by taking this F dash max, the maximum value of the scaled fitness, as C times. C will be the number of copies of highly fit individuals. So C is the number of individuals, or the number of copies of the highly fit individuals that is present in the next generation. C times F dash average, that is the average fitness value of the scaled fitness values, the average value of the scaled fitness values. So for a typical population size n equal to 50 to 100, C is taken in between 1.2 and 2. So it can be 3 also, no problem. It can be enlarged. So you may think how this 1.2 is possible. This 1.2 copies is not possible. But on an average, if you consider some 100 populations, I mean 100 populations, out of the 100 different populations, 12 populations will be having 2 copies, and the rest will be having only 1 copy. So that sort of thing that can be, or 20 populations will be having 2 copies of the same thing, and the rest 80 populations will be having only 1 copy. So that is possible by that is the average value, the average number of copies. So it is 1.2, or it can be 2 also. So that is how the number of copies of a particular individual is controlled. Then there are 2 different cases considered in linear scaling. The first case is initially C is chosen any desired value. Say it is 1.2, 1.3, or 2, or even 3 also. Whatever be the value, we then check whether F min, the minimum fitness value, the raw fitness value, the minimum raw fitness value is greater than CF average. CF average is the average fitness value of the raw average. I mean raw fitness, average value of the raw fitness values. Then C is the constant, that is C is itself. C into F average minus F max. F max is the maximum value of the raw fitness divided by C minus 1. So if F min is greater than this value, then we calculate A and B as F average into C minus 1 divided by F max minus F average. So F denotes, that is the fitness, the raw fitness, not the scaled fitness. In all these cases, we are considering only the raw fitness values, because we are calculating the A and B in order to find out the scaled fitness values. So A is equal to F average into C minus 1 divided by F max minus F average. Then B equal to f max minus c into f average divided by f max minus f average. So this is how the values of A and B are found out when C is when this particular condition is satisfied. That is, f min is greater than C into f average minus f max divided by C minus 1. Then else, if that is not the condition, then A is taken as f average divided by f average minus f min, and B is taken as minus of f average into f min divided by f average minus f min. So this is the condition if this particular condition is not satisfied. If this condition is satisfied, then this is the case of A and B. And if that particular condition is not satisfied, then this is the condition. So in both the cases, we have to fix the C first. The value of C is to be fixed. That we have to choose according to our conditions. So whether it can be 2 or whether it is 1.1. Anyway, 1 cannot be taken. It should be some value greater than 1. Because here is a C minus 1 condition is there. If we take the C minus 1 as less than 1, that is, I mean C less than 1, in that case, this value will become 0 or less than 0. So that is not advisable. So that becomes this particular condition always comes to minus. So that is a difficulty. So in order to avoid that one, we always take C as value greater than 1. Mostly 2. 2 can be taken, no problem. Then if that particular condition is not satisfied, then A and B are calculated using this condition. In the case of case 2, that is we take C as 2. Another way of finding out the value when C is equal to 2. In that case, we consider if f min is greater than 2 times f average minus f min. I have some doubt regarding this particular thing, because f min in the text it is given as f min, but if we substitute C as 2 here, it will be like f min is greater than C 2 times FAV minus f max divided by 1. So I'm not sure whether this one is f min or not. I haven't. I referred many positions, but I haven't got any specific mentions anywhere. So I think what I think is this is not f min, but instead it is f max. So even though in the text it is written like f min, I believe that it is f max. So then, because in this particular text from where I got these derivations, there are some other mistakes also. I tried to correct all those things. So here this f min, I think this is not f min, this is f max. Then the average, the A and B are calculated as A equal to FAV divided by F max minus FAV, and B equal to minus of FAV into F min divided by F max minus FAV. So this is the condition when C equal to 2. So that is about the linear scaling. So when we are doing the linear scaling, the scaled fitness value. So this is the F min and this is the F max. So when it is converted, so this value is fixed. F 2 times F dash average as taken as F dash max. This is F dash max. So this value will be fixed initially, and this value F average is also taken as F dash average. So these two values are fixed initially. This value as well as this value. So this point as well as this point we can fix initially. Then we join these two using a straight line. So then F min, from F min we draw a line upward. So this point can also be fixed. So this is the way the linear scaling under the normal conditions is done. So this can be if the F max is somewhere here. F max is very large value, very large raw fitness value. So somewhere here. So in that case also it can be like this, no problem. So that is the case of linear scaling under the normal conditions. But the linear scaling has some difficulties associated with it unless we take care of those things exceptionally, then there are some problems. So linear scaling may give negative scaling fitness unless special steps are taken. So in the case of, as I said, in the case that is most of the individuals are having very large fitness values and only some individuals are having very low fitness values. In that case, that is if some of those are having very low fitness values and most of them are having very large fitness values like this. So if this is the individuals and these are the fitness values, so if this is the condition, then what will be happening is in most of the cases there is a chance of the fitness, the scaled fitness of these particular individuals being negative. That is a chance. So in order to avoid this condition, that is the negative fitness values, we use the sigma scaling. So the sigma scaling or the sigma truncation helps to overcome this problem. What we do is the sigma scaling keeps the baseline near the average. The baseline is the lower value, the lowest value. The lowest value is kept near the average value. So the setting the baseline S standard deviation, that is S times standard deviation below the mean, where S is the scaling factor. S is considered as the scaling factor and sigma is the standard deviation of the fitness values. So what we do is we keep the baseline, the lowest fitness in the scaled fitness values is taken as S times sigma. So the individuals which are having fitness below this particular value is taken as having a zero fitness value. So that is those individuals will be truncated or removed from the population. That is the condition. So like this, the sigma truncation or the sigma scaling discards such of the average members. That is the below the average values are there or the below the baseline values. The fitness values are below the baseline values. In that case, we remove those members. So then the linear scaling is applied to the remaining members. So that is the condition. So we calculate F double dash as F minus F average minus S sigma. F average is the average raw fitness, minus S is the scaling factor, and the sigma is the standard deviation of the average, the standard deviation of the raw fitness values. Then F average minus S sigma is calculated and it is subtracted from each of the F values, each of the fitness values. Then that particular value is taken as F double dash. If this value is greater than 0 or if this value is positive, then we take it as the same value itself. Otherwise, we give 0. That is, if RHS is greater than 0, that is, if F average minus S sigma is greater than 0, then we take F double dash as this value itself. Otherwise, we take it as 0. So after this, linear scaling is applied. So F dash is equal to a F double dash. In this case, we use F double dash, this particular value, instead of the raw fitness. So in some cases, it will be 0. So where the lower fit, the individuals will be having very low fitness. So this F double dash will be 0 in that case. So this avoids the danger of negative fitness. Anyway, even if the individuals is having a 0 fitness, the B will be present there. So B is a positive value. So obviously the danger of negative fitness values is avoided. Then the last fitness scaling procedure, that is the power law. Power law is very simple. Actually, we are raising the raw fitness to a specific power. The power value, that is the scaled fitness F dash is equal to F raised to K, and K is the problem dependent constant. It can be any value greater than it can be any value, but normally it is a value that is normally taken as 1.005. So that is this is a possible value. I am not saying in all the cases it should be the value, but this value is given in literature in the textbook, that is it can be taken as a value for K. So In this case, the fitness values are raised to some powers, that is k. But here also there is a problem of the fitness values being very wide range. If the fitness value of some particular element or some particular uh, individual is very large value and some others is having a very low value. In that case, when if we raise it to the power, the difference increases actually. So the power law is not much used actually. So the best scaling procedure that is used, that is having no problems, is actually sigma scaling. But the linear scaling can be used with some